Hi, in this lecture we will start with geodetic satellite techniques and then continue to another space geodetic technique which makes use of natural objects in space. Besides global navigation satellite systems where satellites transmit signals, there exists a reverse configuration, which means that the ground receiver transmits signals and satellites receive those. DORIS, which is the acronym for Doppler Orbitography Radio Positioning Integrated by Satellite, is a French satellite system. It was originally designed for the determination of satellite orbits, but can also be used to determine positions of a ground station, given that precise orbits are available by other means. In the case of DORIS, ground-based radio beacons emit a signal which is picked up by receiving satellites. A frequency shift of the signal, also known as Doppler shift, is occurring due to Earth's rotation and the satellite's own velocity. Onboard electronics measure this Doppler shift, which is then downloaded from the satellite to a ground center where it is processed further. This allows to deduce ground positions as well as other parameters when analyzing many Doppler observations together. Satellite laser ranging, SLR, is another system which has transmitters on Earth and makes use of satellites. Instead of radio waves, short but strong laser pulses are shot to satellites which are equipped with reflectors that bounce the laser light. The ground station measures the round-trip time for a pulse to be transmitted, reflected, and travel back to the station. As laser signals travel with the speed of light, we can multiply the measured time with this velocity and obtain twice the distance between the station and the satellite. Unlike GNSS, station and satellite clocks do not matter, and we are able to directly obtain the geometric distance between the ground station and the satellite. Such measurements can be made with millimeter-level precision. The use of several ground stations which shoot laser pulses to the same satellite makes it possible to derive station positions as well as satellite orbits. As we have learned earlier, satellite orbits are disturbed in correspondence to the Earth's gravity field. Therefore, measuring these deviations with the help of SLR allows us to compute parameters of the Earth's gravity field by observing a test mass, in this case a satellite orbiting the Earth, high above the surface of our planet. Several satellites are equipped with reflectors that allow SLR observations, and it is no surprise that GNSS satellites belong to this group of satellites. Therefore, GNSS orbits can be monitored by means of SLR, or SLR-derived orbits can be compared with GNSS measurements. You see, space geodetic systems start to complement each other. A special application of laser ranging is called lunar laser ranging, where the moon is used instead of artificial satellites, and particularly strong lasers are necessary. The American and Russian space programs in the 60s and 70s included the deployment of laser reflectors on the moon's surface. They have ever since been used to measure the distance between the ground stations on Earth and the moon's surface. Since we know the moon's orbit very well, we can use it like a satellite and determine coordinates on the Earth. We have now seen that space geodesy makes use of both natural and artificial objects in space in order to determine parameters of the Earth. However, there is one space geodetic technique which goes even further and uses objects at the outer edge of the universe to measure properties of our planet. This method is called Very Long Baseline Interferometry, or VLBI, and utilizes large radio telescopes like this one at the Onsala Space Observatory in Sweden. One telescope alone isn't sufficient to make VLBI observations, but using two or more telescopes located at different places around the globe turn VLBI into a very powerful instrument for observing our planet. A signal from a very distant quasi-stellar radio source, or quasar, is collected at multiple radio telescopes on the Earth. Since the quasar is so far away, we can assume that plane wave fronts, which allows a simple concept for VLBI. All we need to do is measure the time when radio waves pass a certain telescope and compare it with the time the same radio wave has reached another telescope. As we know the angle under which we see the radio source, the travel time, also called delay, between the telescope can be then translated into the distance between the two telescopes. This distance is referred to as baseline length. If we observe several different radio sources, they will appear under different angles on the sky, which means that we will not only be able to get the baseline lengths between the telescopes, but also be able to determine the complete 3D vector between them. Long before the first GPS satellites, the use of VLBI stations confirmed the theory of plate tectonics. The stations were located at different tectonic plates and showed evidence of the seafloor spreading in the Atlantic Ocean that forces the Eurasian and the North American plates to drift apart. When we look at the baseline length change between Westford, a VLBI station in the US on the North American plate, and Onsala, a VLBI station in Sweden on the Eurasian plate, we see that there is an almost linear trend of increasing distance. It increases by almost 2 centimeters every year, and this is an effect which has become visible thanks to the improved VLBI precision over the last decades. This also holds true for other space geodetic techniques. It's now possible to determine positions with a few millimeter precision almost anywhere. Furthermore, monitoring the positions in a long-term perspective allows us to determine the movements of certain regions or continental plates in general. Very good. Thanks for watching this lecture about space geodetic techniques. I hope you enjoyed it. Stay tuned for more lectures.